Right. So in the previous session we have seen about synchronous and asynchronous counters that count from 0 to 15. 4-bit binary counter. Right. So that is an up counter. Now we will see a down counter, 4-bit down counter. So I mean, this is actually required in digital multimeters, where the readings may be rising up or falling down. So both ways the device has to count. Okay. So now, the up counter circuit we have seen already. Let's say asynchronous counter, the output of each level is given as input to next level. So here we are taking either JK flip flop with 2 inputs maintained at 1 or a T flip flop, and input should be high. Right. So both J, K inputs are maintained at 1 for all the flip flops. So you have to be very careful while mentioning the junctions. Okay, so this is a asynchronous up counter. This is up counter. So here initially all bits are maintained at 0, and once you start giving the clock pulse, each counter will change its state to count the numbers. Now, to design a down counter, we have to take the output from the other end. Like, let's say if this is Q and Q bar, you have to take output from Q bar and give it as a clock pulse to next level. So we just have to make a reverse configuration. So all initial states are at 1, and output of Q bar state is given as input to next level, and given as clock to next level. So as usual, output is taken at here. Now let us see the timing diagram for 16 clock pulses. So taking 16 clock pulses and edge trigger. There are two types of flip-flops. One is level triggered, another is edge triggered. For all counting purposes, we will be using edge triggered flip-flops. So initially, all outputs are set to 1. So Q0 is also at 1 initially, and by the end of the first clock pulse it goes to 0. So at the end of each clock pulse Q0 changes its state. Right. So Q0 changes its sign for every falling clock pulse. So that part is clear. Now about Q1. So the input for second flip flop is taken from Q bar, Q0 bar. So Q bar becomes high when Q is low. So when Q0 is low, Q bar is high, and at the edge. So at the rising edge, Q1 changes its state. Right? So when Q0 is at the rising edge, Q1 changes its state. So Q1 is already at high state and goes to 0. Again 1, 0, 0. That's about Q1. Here also for the next level we have to see the rising edge. So Q2 changes sign at the rising edge of Q1. So Q2 is already at high initially, and that goes to 0 at the rising edge of Q1. Same rule applies even for Q3. Q3 changes its state at the rising edge of Q2. Initially it is set at 1. That's all. Well, if you give numbers, it will be 1 1 1 1. At the end of first clock pulse, 1 1 1 0. At the end of second clock pulse, 1 1 0 1. Like that, you'll get a down counter which starts counting from 15 to 0. So the same way you can design a synchronous down counter. So this is asynchronous down counter. Same way you can develop synchronous down counter. Synchronous down counter. For synchronous counters, clock pulse is common for all, and output of each flip-flop is given as input to next level. Clock pulse is common and output of each level is given as input to next level. And we have to follow the same rule. Q bar should be given as input to next level. Right? So clock is common. Q bar is given as input to next level. And output is taken as usual at Q's. That is a synchronous down counter. Timing diagram is as usual, same as a synchronous counter. Next one is up down counter. So the same counter has to perform the operations of both counting up and counting down. So we have to choose the option when to give a trigger for up counter and when to give a trigger for down counter. So there will be an additional input for up choice and down choice, and we have to use it as a trigger. So I consider up as 1 and down as 0. So then I develop this asynchronous counter. So if the choice is up, I have to trigger Q. So if the choice is up, I have to trigger Q. So when up is 1 and given previous state output is 1, it will trigger the next level. So when the up state is 1 and previous stage output is 1, then only the clock will reach the next stage. Then for the down state, we have to pass on the Q bar output. So down state is 0. So we have to develop one out of it. The same clock, we are forwarding Q bar when the down state, when the up down status is 0. here all JK inputs must be maintained at 1. So JK Q1. So output is as usual taken at Q0, Q1, Q2, Q3. And since it is a asynchronous counter, all inputs are maintained at 1. And the clock trigger is taken from previous output Q or Q bar, depending on up or down inputs. The final one is modulus counter. That's a modulus 10 counter. So it is a most useful counter for all digital gadgets which count in decimal system. So after counting from 0 to 9, the counter has to reset to 0 again. So if it is a binary counter, it will count all A, B, C, D, E, F up to 15 numbers. But for BCD counters, we require a counter reset after 9. So counting from 0 to 9, then when 10 comes, the counter has to reset. So there are set and reset buttons for each flip flop. I mean they are not shown here because they are not used here. There is a set button and a reset button for every flip flop. So now I am going to use that. So modulus 10 counter, it counts up to 9. That means what? 1001. So this is 9 and 1010. This is 10, and when that count comes, everything should be set to 0. Right? So that we will see. So I am taking 4 flip flops. And I am designing an up counter, asynchronous up counter. So each output is given as input to next level. Each output is given as input to next level, asynchronous up counter. And all JK inputs are maintained at 1. All JK inputs are maintained at 1. Now we have to use an additional condition. And when the counter counts 1010, everything should be set to 0. Then we have to trigger the reset button. So what should we do? So this is Q3 and Q1. When both Q3 and Q1 are 1, and Q2, Q0 are zeros. So this is Q0, Q1, Q2, Q3. So at ensure Q3 and Q1 should be 1 and Q2, Q0 should be zeros. So I am taking Q0 bar Q0 bar, direct Q1, then Q2 bar, then direct Q3. I am collecting all the 4 conditions and I am giving them to an AND gate. Q0 bar, I will get 1, Q1, Q2 bar and Q3. So when all are 1, the output of AND gate will be 1 and I will give that output to reset button. So this is set and this is reset. So I have to give the output of AND gate to all reset buttons. And I have to choose the condition wherever we want, whatever we want. Let's say in this case it is 1010. So when the counter counts 1010, all the required outputs are sent to the AND gate and the output of AND gate is sent to reset button. So this is used in BCD counters where the count goes from 0 to 9 and after counting 9 the counter resets to 0. So let's say you have to design a digital clock. So what do you do? The seconds counter, the first digit will count from 0 to 9 and after counting 9 it will reset to 0 and the next digit increases, right? So here we have to use a mod 10 counter. So this is a mod 10 counter. And for the second digit, it has to go from 0 to 5. after counting 59, the counter resets to 0, 59 seconds. So here we have to use a mod 6 counter. So mod 6 counter means what? We have to see where we get 6, like 0, 1, 1, 0. So we have to give those outputs to the AND gate. So what you have to give? Q3, Q2, Q1 and Q0. So we have to give Q0 bar, Q1, Q2, Q3 bar. So these are the inputs that you have to give to the resetting AND gate for mod 6 counter. So mod 6 counter counts from 0 to 5 and resets when the counter goes to 6. So we require two such counters, one for seconds counter, another for minutes counter. Next one, hours counter. So here also you require a decade counter 0 to 9, and the next counter instead of 0 to 9 you can directly go up to 0 to 12 directly. So it is a Modulus 13 counter, but you won't get any digital output, right? So we have to use BCD. I mean, after counting 9, the counter has to reset to 0 and it should display 10. So here you need a 0 to 9 counter, decade counter, followed by zero to 1. But you require a special case that when this second digit is 1, the first counter has to go up to 2. I mean, after counting 12, it has to reset to 0, 0. When the second digit is 0, the counter has to go up to 9, and when the second digit is 1, it has to go up to 2. You may require an additional condition over there. So we have to configure both of them together. Here each counter is configured separately. 0 to 9 a decade counter, 0 to 6 0 to 5 another mod 6 counter, mod 10 mod 6, here mod 10 mod 2, but these both counters should be configured together. When you have 0 here, this counter should count up from 0 to 9. When you have 1 here, it should count from 0 to 1. So after counting 11, it should reset to 0. Otherwise, if you are counting in a 24 hours clock, after counting 24, it should reset to 0. So I can design each block separately and connect them together to develop a digital clock. So that can be done in SEDAR app.